Welcome to Architect of Tomorrow. We don't just write code here, we design the systems that run the world.
All right, let's talk about something that's driving AI developers nuts. You've poured months, maybe even years, into building this absolutely brilliant AI agent. It thinks, it reasons, it's a masterpiece, but then you deploy it, and in the real world, it's just slow. Painfully slow. Today, we're going to pull back the curtain on the hidden bottleneck that nobody ever talks about. It's the big question, isn't it? It's so frustrating. You know your LLM inference server is screaming fast, maybe just 150 millisecond latency. And yet, the end-to-end agent experience just feels sluggish, like it's wading through mud. So if it's not the model, what on earth is really going on here? Let's just break down how quickly the time vanishes in just a single reasoning step. So the agent thinks that's about 100 milliseconds on a local GPU. Okay, not bad. But then it has to send a request out over the network. Boom, 50 milliseconds gone. The function executes, but maybe it's waiting in a queue. That's another 200 milliseconds. Then the result has to travel back, add 50 more milliseconds. And finally, the agent has to process that result, another 100 milliseconds. And just like that, you've burned through half a second. Now, I know what you're thinking. Half a second doesn't sound like a catastrophe. But what if your agent needs, say, 10 of those steps to do something simple? All of a sudden, you're looking at 5 seconds. For a user, that is an eternity. And remember, that's for one agent. Can you imagine trying to run 1,000 of them at once? The whole thing just grinds to a halt. So where is the real problem? Well, if you're pointing the finger at the large language model, I'm here to tell you you're looking in completely the wrong place. The real culprit is actually hiding in plain sight, right inside the very architecture of our systems. See, here's the root of it all. Our systems are basically cobbled together from these different parts that were never designed to work together for AI agents. Your AI compute, that's optimized for one thing, maximizing token throughput. The network, it's optimized to slash costs. In your data services, they're all about consistency. The problem is, these goals are constantly fighting each other. And this fight, this conflict, it creates a crisis. Our current setups force us to constantly shuttle these enormous chunks of data back and forth across these expensive, slow networks. All so the GPU can have a little think for a moment. The network basically becomes a giant parking lot, and your brilliant agent, it's just stuck in traffic. In this chart, wow, this really shows you the scale of the problem. When you actually stop and measure where the time goes, you find something pretty shocking. The reasoning, the bit everyone obsesses over, that's only about 30% of the delay. A whopping 70% of your agent's time is just wasted, waiting on the network and waiting for data. But hey, it's not all bad news. There is a solution. It's this really powerful new architectural playbook, and it's called Compute Network Co-Design. It's all about getting these separate, warring components to finally work together as one lean, mean, efficient machine. So, the very first principle is called placement. And the idea? It's so simple, but it is profound. Stop moving all your data to the compute and start moving your compute to the data. You know the traditional way, right? You've got this one big centralized GPU cluster in a data center somewhere, and everything has to phone home to talk to it. That creates a massive, massive bottleneck. The co-designed way flips that on its head. You distribute smaller compute resources out to the edge, putting them much closer to where your data actually lives. And the results? They are just staggering. A typical round trip to that central cluster might take you 200 milliseconds, but by moving that compute out to the edge, that very same round trip can drop to just 20 milliseconds. That's a 10x speed up right there, just by changing the location. Incredible. Okay, on to the second principle. This one tackles bandwidth, and it asks a really simple question. What information really needs to travel across that network? I'll give you a hint. It's almost always way less than you think. So instead of streaming these huge 50 megabyte database records for your agent to sift through, you do something smarter. You pre-compute summaries, like vector embeddings, which are tiny. Then the agent can just ask for the most similar items, and the network only has to send back this tiny 50 kilobyte payload. So what does that mean in the real world? It means that by just being smarter about what data you send, you can suddenly handle 100 times more agents on the exact same network infrastructure. That is a massive, massive gain in scalability, and you didn't have to spend a single extra dime on bandwidth.
All right, principle number 3 is all about protocol. This is about how your different services communicate with each other, because the traditional way creates this hidden traffic jam that slows everything down.
So the old school approach uses synchronous communication, right? Like a REST API call. The agent sends a request, and then it just sits there. It waits. It can't do anything else until it gets a response. The co-design way uses event streaming. The agent just fires off an event saying, hey, I need this, and then immediately moves on to other tasks. When the result is ready, it'll handle it. No more idle time. And by getting rid of all that wasted waiting time, a single machine can all of a sudden juggle the requests of 10 times more agents. It's a fundamental shift, really, from a one-at-a-time process to a massively parallel one. And that brings us to our final principle, state locality. This is all about the agent's memory. Where does it live, and how fast can the agent get to it when it needs to remember something? The old way is to keep the agent's state in some central database. So every single time the agent needs to remember something, that's another slow, painful network round trip. The co-designed approach keeps the agent's working memory in a super fast local cache, giving it microsecond access times. Then that cache gets synced back to a central store to make sure it's durable. You get the best of both worlds, lightning speed and safety. And look, this isn't just some theory. Check out Microsoft. Their Azure agents run at twice the speed of their competitors. And you want to know why? It's not because they have faster GPUs. It's because they have a better architecture, one built around these exact co-design principles. Or take a look at Meta. They're deploying their reasoning models to edge data centers so that users are interacting with agents locally with latency as low as 10 milliseconds. And the result? An instant user experience. That is a game-changing competitive advantage. But here's the really sad part. Most companies out there building agents, they don't even measure this stuff. They just assume their agent is slow because the model is slow. So what do? They throw more and more money at bigger, faster GPUs. And guess what? Nothing changes. They are trying to solve the completely wrong problem. So how can you avoid falling into that same trap? Well, here is your action plan. This is how you start thinking like a co-designer. First, measure your latency. You have to find out where the time is actually going. Second, test deploying some of your compute on the edge. Third, implement vector search to shrink those data payloads. And finally, you got to profile your network traffic to find out where the waste is. And this really brings us to the final crucial question you need to be asking yourself. You've been so focused on optimizing your models, spending all this time and money. But what if the real bottleneck, the one that's costing you performance, users, and a fortune, has been your network all along?